Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, the other day was the Equinox, and I took the opportunity to measure the circumference of the Earth. I thought I'd go through that and share some findings from my friend B-Ball for Life in Hawaii. By the way, in case you're curious, behind me is my astronomical binoculars. Now, as you can see, they're a pretty good size instrument. They're 20 by 100 millimeters, and they only run about $200. The stand is far more than that. But the point that I'm making is that you don't need special equipment to do astronomical observations. You just need a decent set of binoculars and some sharp eyes. I can easily see the moons of Jupiter, the rings of Saturn, and I can see a lot of deep sky objects such as the Andromeda Galaxy and the Orion Nebula using these binoculars, and you can do that at home. Science is not something that has to be done in a lab. You can easily do it at home with very simple equipment. Now, for example, my friend B-Ball for Life did the same thing in Hawaii. All he did was look around the house and saw some objects that he had. He had a couple of dumbbells, he had some pieces of wood, and he went outside to a relatively smooth surface, the sidewalk in front of his house, and he was able to measure the circumference of the Earth. Likewise, I was working the day of the equinox, and I didn't have much time, so at 1:56 p.m., which was solar noon, I just took the nameplate off of my desk, taped a couple of pieces of paper to the hardwood floor in my waiting room, and when it cast a shadow, I just marked where the point of that shadow was, and I measured it with a tape measure. From that, I was able to get the circumference and the radius of the Earth to very good accuracy. Let's see how I did it. Now, the method Eratosthenes depends on a couple of different things and some basic assumptions. For example, you do need to know a spot that is directly underneath the sun. This is a stick that would cast no shadow. And then what you do is you look at other shadows and measure the angles of the shadows that are cast by the sun. Now, a very interesting thing is that if the Earth was flat or spherical, you could easily predict what these shadows would look like, and then you could test those predictions. Now, the other thing that you have to look at is the sun local and the rays divergent, or is the sun very distant and the rays are coming in parallel? Now, by the time of Eratosthenes in about 300 BC, the fact that the Earth was a sphere and had a curved surface was well accepted. However, you don't need to make that assumption. The other thing that you have to look at is, are the rays of the sun parallel or are they divergent? Now, it's very easy to tell if the rays of the sun are coming from a distant object and arriving at Earth in parallel, or they're coming from a local object and coming in divergent rays. Now, the other way is probably a little bit more elegant. All you need is a tennis ball. Hold it up to the moon and compare the phase of the sunlight on the tennis ball to the phase of the sunlight on the surface of the moon. Obviously, the moon will have to be up during the day to do this. If they're the same, the sunlight is approximately parallel. If they are different, it's divergent because it's a local sun. But the absolute proof is in the mathematics. We should be able to predict each of these angles on a flat surface, and we can also predict each of these angles on a curved surface, given both a local sun coming in with divergent rays or a distant sun coming in with parallel rays. All we have to do is compare our results. For example, we could triangulate the distance to the sun using any of these triangles. We have one here, and one here. Since there's only one sun, it will all come back to the same elevation over this particular stick right here. Whereas if the Earth is curved, you will not be able to triangulate the distance to the sun because the rays are coming in parallel. In fact, at each and every one of these locations, if we try and triangulate it, it will come back to a different distance. So the bottom line, although we are very comfortable in our understanding that the Earth is a sphere and that the rays of the sun are parallel, we don't have to make that assumption. We can actually test for it, make a prediction on both models, and test it against reality to see which one is right. So let's go over the results real quick. This is a page called Math Portal. And this is the right triangle calculator with detailed explanation. What we want to find is angle beta here. This is the angle of the shadow. All we have to do is put in side A, which is going to be the length of our stick, and in my case it was 10.37 inches. And then leg B is going to be the length of the shadow, and in my case that was 10.625. And ask it to find angle beta. So let's go ahead and do that. And here it is right here. So it comes back to angle beta as 45.6821 degrees. Now this is within 1 degree of my latitude at the time of this experiment, and here's how you find it. Now I actually do the math on my community page on my YouTube channel, and as you can see, here are my results, and I've got the numbers in it. 45.6821 degrees. The distance to the equator is 5,070.71 kilometers. And my calculated circumference is 39,960 kilometers. The actual accepted circumference of the Earth is 40,075 kilometers. And I was 115 kilometers off. I calculated the radius at 6359. And it's actually 6371, or with a difference of about 12 kilometers. Now recall that one of our purposes in this experiment was not only to measure the size of the Earth, but try and get some actual numbers to decide if the Earth was flat and the Sun was small and local, or the Earth was spherical and the Sun was very distant and the rays were arriving in parallel. And the way that we were going to do that was to try and make some predictions here. So the first thing that we're going to do is we'll take this alpha 2 right here. The middle one is about a 45-degree angle, and that kind of corresponds to where I am. So what we're going to do is we're going to triangulate the distance from the Sun using the distance to the equator and the angle of that shadow. So let's go ahead and do that real quick. Now, one way that we can determine whether or not the Earth is curved or flat is we can simply look at another location. And as you recall, my friend B-Ball for Life did it in Hawaii using this apparatus. Let's go ahead and look at his numbers. Once again, the distance from B-Ball to the equator is 2269.64 kilometers. And angle B formed by the shadow is 22.249 degrees. Let's solve for leg A. And there it is, 6,036.91 kilometers. Now notice that's different than my value of 4,951.68 kilometers. It's almost as if the Sun was in two different locations. The only other alternative explanation is that the Earth is not flat. So if I'm alpha 2 at 45 degrees and B-Ball is alpha 3 at 22 degrees, even though we have different angles on a flat surface with a local sun, we should be able to triangulate back to the same spot above the equator. That does not occur. Now, skeptics may argue that with a very distant sun and parallel light rays, it would be impossible to tell the difference between a curved surface of the Earth and a flat surface. That's really not the case, because we do not find our position on Earth using shadows and sticks. We use very precision instruments such as this marine sextant. Now, on a bad day, this marine sextant will find your latitude within about 5 kilometers. My stick experiment found my latitude within 1 degree. So the bottom line is there will be a significant difference between sextant readings on a flat surface versus a curved surface. Another thing that I want to discuss is some of the corrections that need to be made to find your location, or specifically your latitude on Earth. For example, when I took my readings at solar noon in Marquette, Michigan, it was several hours after the true equinox. The true equinox on that day was at 5:40 a.m. my time. That was when the sun was directly over the equator. By the time I did my observation at 1:56 p.m. in Marquette, Michigan, the sun had moved north of the equator by 1 minute and 20 seconds. When you're dealing with a sextant, you actually have to take those small corrections into account, and that's one of the reasons that you can find your location anywhere on Earth that you can see the sun or the stars within just a couple of kilometers versus 115 kilometers like my error was. Now, in a future episode, we're going to have another look at the sun. While everybody talks about doing the Eratosthenes experiment on the equinox, it's just simply the easiest to do on that day. You can do it any day of the year. Now, another thing that you can do with the sun and a stick is you can actually find cardinal directions. We're going to do this in a couple of weeks when I set up the pier for my telescope, because it has to be aligned along true north and true south. And I'm going to show you how we're going to do that simply using a flat plate and a nail. So until then, this is Bob the Science Guy signing out for Northern Michigan. Make sure you hit that like and subscribe, and our channel always likes your support. So, thank you very much for stopping by, and take care.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.